Okay, so let's start. Hello, everyone. Welcome. My name is Susana. I'm a senior communications specialist at the ICCT. Thank you for attending today's webinar. As you maybe have heard when you joined the webinar, this webinar is being recorded. We will be making it available on our YouTube channel in the coming days. So today we are going to talk about our newly launched report. The title is Life Cycle of Greenhouse Gas Emissions from Passenger Cars in the European Union, a 2025 update and key factors to consider. The report is available on our website and you can download it via the link that we will be sharing on this chat. Our speakers today are Dr. Marta Negri, researcher at the ICCT, and Dr. Georg Bieker, center lead at the ICCT. And here's a brief look at what we'll be covering today. We will begin with a presentation on the key findings. Marta Negri will open with an overview of the study's scope and methodology. And following that, Georg Bieker will place these findings in the broader policy context, exploring how they relate to the European Union's transition toward a zero-emissions automotive sector. Presentations will last around 25 minutes and we'll have an additional 15 minutes to answer your questions. So please don't forget to write them in the question block in the control panel on your screen. And yes, so that's the housekeeping rules for today. And before we start, we have an announcement. This is especially for our European audience. We will be in Brussels in September, on the 22nd of September. We will be launching an important report, the EV Transition Check. And this report will offer a comprehensive overview of the European automotive sector's progress towards zero-emission vehicles. This will be published in anticipation of the European Commission's first progress report on the CO2 standards for cars and vans, and it will provide crucial data and analysis to inform the 2026 midterm review. So you are of course invited to come, and you can find the link with more information on the chat. So with this small announcement, we now move to the presentation of today's publication, and I will pass the floor to Marta, please.
Yeah, hi everyone. I'm very excited to be presenting the results of this study. I will start with an introduction on the methodology and key input data that we've used for the analysis, and present the key results that we had, and finish with a summary. And after that, Georg Bieker will continue with policy considerations. As for methodology and input data, so we've analyzed vehicles, the emissions during the life cycle of vehicles registered in 2025, focusing on the EU average medium-sized passenger cars. And we've analyzed different powertrain types, in particular gasoline, diesel, natural gas, internal combustion engine vehicles, hybrid and plug-in hybrid vehicles, battery electric vehicles, and fuel cell vehicles. We've used real-world fuel and electricity consumption, considering a lifetime mileage of 240,000 kilometers over 20 years. And I'll get back to these input parameters. And we've also accounted for the dynamic change of electricity and fuel mix during the lifetime of vehicles. As for the fuel and electricity consumption, we've considered for most powertrains 2023 EU registrations weighted averages, with the exceptions of hybrid vehicles. For those, we have considered the Toyota Corolla as representative vehicles, and it is the model that dominates hybrid vehicle sales in the medium segment in the EU. And for fuel cell vehicles, we've considered the Toyota Mirai, which is the only fuel cell vehicles model sold in the segment. As I was mentioning, we consider real-world fuel and electricity consumption. This means that we've corrected the official test values with the real-world data that is seen. In particular, we've used the European Environment Agency data collected for gasoline, diesel, and plug-in hybrids, and we see that there is a variation between 18 and 25% gap, so higher gap compared to WLTP numbers for gasoline and diesel vehicles, and in particular for plug-in hybrid vehicles, we see a difference of 239% So higher fuel and electricity consumption values compared to WLTP values. So we've used these corrections to account for real-world use. Similarly, for electric vehicles, we've considered a 25% gap between official test values and real-world conditions. For the lifetime fuel and electricity mix, we consider as our baseline case the JRC potential CETO scenario for 2024, but we've added also sensitivities using the International Energy Agency scenarios, both the stated policy scenario and the announced pledge scenarios. And these three scenarios are reported in the graph that you see on the right-hand side. For the fuels mix instead, we've used as our baseline case a fuels mix that is based on RED 3 requirements, but we've also added sensitivities accounting for a more optimistic advanced biofuels uptake in the mix. As I was saying again, for the full vehicle lifetime, we've considered 20 years that we see reported by several member states as a representative lifetime of vehicles. During this lifetime, the annual mileage is on average 12,000 kilometers, which results in a lifetime mileage of 240,000 kilometers. We've also included the indirect land use change emissions that can be significant, especially for some of the biofuel pathways, as you can see in the chart on the right-hand side. This allows for a more comprehensive assessment of the total climate impact of fuels, as it can substantially increase the overall carbon footprint of biofuels. Finally, for the electricity generation, we've considered also the infrastructure emissions, meaning the emissions related to the construction of the power plants and grid connections. And as you can see from the table, this can be particularly significant for renewable energy sources, and it can be up to 100% in this case. It's less relevant for the non-renewable electricity sources. So we've included the entire life cycle emissions of electricity production. And finally, to the key results. This is our baseline case. So this includes the baseline results using the assumptions that we consider being most representative. As you can see, so in this chart shows the emissions intensity along the life cycle for all the powertrain types that we've considered. Starting from the left-hand side, we have gasoline vehicles, considering the biofuels plants, diesel vehicles, natural gas vehicles, hybrid and plug-in hybrid vehicles, battery electric vehicles, both with the average grid mix in the European Union and considering only renewables. And finally, fuel cell vehicles, both considering renewable hydrogen and considering natural gas hydrogen. The bars in gray represent the vehicle manufacturing emissions. As you can see, these are more or less the same for all powertrain types. But when we account for the battery manufacturers, so the dark yellow bars, these are, of course, we get higher emissions for battery electric vehicles. Excuse me. So this, the production of the battery makes it so that there's a gap of about 40% higher emissions for battery electric vehicles compared to other powertrain types. But this is more than compensated for during the use phase of vehicles. And this is represented by the bars in dark blue and light blue that represent fuel consumption, respectively, and fuel production. The light yellow bars instead are electricity production. So as you can see, overall, during the life cycle, battery electric vehicles have about 73% lower emissions compared to gasoline cars. And this becomes 78% lower emissions compared to gasoline cars when battery electric vehicles use only renewables. Fuel cell vehicles have about 50 grams of emissions per kilometer, and this is 78% lower than gasoline cars, but only when using renewable hydrogen, which is not widely available for in Europe. And instead, when using natural gas hydrogen, the emissions reduction is only with 26% lower compared to gasoline cars. Considering instead hybrids and plug-in hybrids, these have respectively minus 20 or 30% lower emissions compared to gasoline cars. So we see that there is reduction potential, but is not as significant as for battery electric vehicles. We've also analyzed a sensitivity scenario, as I mentioned before, taking into account an optimistic uptake of biofuels. In this case, we've considered a doubling of the volume shares of biofuels for the diesel mix, and for the ethanol mix, so the gasoline mix, a volume share of ethanol that reaches the maximal technical limit, that is 10% in volume. So even when assuming a more advanced or more optimistic uptake of biofuels, we see that the reduction in emissions for internal combustion engine cars is not that great. So we have an emission reduction from 0.5% to 2.6%. Account for a change in results when changing the key parameters that we've used. So we've considered 5 main factors to see what changed when changing, again, these parameters. For the first analysis, we've considered, instead of accounting for the dynamic change of fuel and electricity mix over the lifetime of vehicles, we've considered a static fuel and electricity mix. And in the chart here, you see that compared to our baseline scenario that's represented by the dotted bars in gray, the emissions for plug-in hybrid electric vehicles and battery electric vehicles change quite significantly. So when accounting only for a static fuel and electricity mix, meaning accounting for only the 2025 situation and not accounting for a change in the future, plug-in hybrids have 13% higher emissions, and battery electric vehicles have 58% higher emissions. So this largely overestimates the emissions for battery electric vehicles. Again, because the expectation is that the electricity mix will decarbonize over the time. For the second factor, we've instead of using real world fuel and electricity consumption, we've used WLTP, fuel electricity consumption. And again, the dotted bars in gray represent the results in our baseline case. And this chart instead shows how the results would change when using WLTP fuel and electricity consumption values. As we can see, quite notable, the gap between real world and official test values is higher for plug-in hybrids. In particular, when using WLTP fuel and electricity consumption, the overall emissions for plug-in hybrids are underestimated by about 50%. So this is quite significant. For internal combustion engine vehicles, so gasoline, diesel, natural gas, and even hybrids, the emissions are underestimated by between 12 and 14%. And instead, for battery electric vehicles, both when using the average grid mix and the only renewables mix, emissions are underestimated change between 2 and 5%. So this is to show that using real world values makes a more representative comparison. For the third factor, we've considered, instead of a full vehicle lifetime of 20 years, that's our baseline case, we've considered the lifetime of 15 years. And again, in this case, we see that emissions for all the powertrain types are overestimated compared to our baseline case that I guess again is shown with dotted lines. However, this change in emissions is higher for battery electric vehicles that are 22 to 28% higher compared to our baseline case. And this is because the higher emissions during production of vehicles has fewer considered years to be compensated for during the use phase. We've considered instead, not considering the indirect land use change in the calculations, makes it so that the emissions are overall underestimated by, from 1 to 2%. So in case of Europe, the land use change emissions do not make a large impact on the life cycle emissions of vehicles However, in other regions where there's higher use of high ILUC risk biofuels, for example, this accounting for ILUC emissions is important and has more substantial impact on the overall emissions of vehicles. When combining all these factors, the emissions, the life cycle emissions of powertrains can change quite significantly compared to our baseline case. In particular, what is quite notable is that for plug-in hybrids, in this case, the emissions would be underrepresented by 32%, and the emissions for battery electric vehicles are overestimated by 64%. And this makes it so that emissions for plug-in hybrids and battery electric vehicles seem comparable. While in our baseline scenario, the emissions for plug-in hybrids are almost 3 times higher than battery electric vehicles. Emissions intensity for combustion engine vehicles are instead underestimated by from 7 to 11%. Finally, again, we wanted to show the impact of the infrastructure of electricity generation emissions, so accounting for the fact that renewables need to be constructed and built and connected to the grid. And this is accounting for infrastructure generation emissions is particularly relevant for e-fuels. And in this case, that's represented by the last bar chart on this chart. And in this case, for e-fuels only vehicles, these emissions can account up to 38% of the overall life cycle emissions. This study comes after a series of other LCAs that the ICCT performed. We've left the link and reference to the studies that we've conducted before. To summarize, we see that the electricity mix is getting cleaner. Vehicles LCA should represent this expected decrease in emissions intensity of the electricity mix to make a representative comparison across powertrains. The gap between WLTP and real-world fuel and electricity consumption should be accounted for, as this gap is particularly wide for plug-in hybrids vehicles, and so real-world values should be preferred when performing LCA analysis. Finally, we see consistent evidence that vehicles in the EU have a lifetime of 20 years or more, and so a full vehicle lifetime should be accounted for when doing these analyses. And this is to account for the long-term benefit of a cleaner grid and not overestimate the relevance of production emissions. Finally, as we've seen, ILUC emissions can increase the climate impact of biofuels and should therefore be included in the analysis. And finally, the electricity generation infrastructure emissions should also be considered, especially for powertrains that use e-fuels only, for example. To summarize again, the key results that we got in our baseline case, battery electric vehicles on average have 73% lower emissions over their lifetime compared to gasoline cars. The higher production emissions that battery electric vehicles have are more than compensated for already after 1 or 2 years of driving. Hybrid and plug-in hybrids only have about 20 and 30% respectively lower emissions than gasoline cars. So although there is some benefit from the climate perspective, their life cycle emissions are still 3 to 4 times higher than battery electric vehicles. And finally, fuel cell electric vehicles show a similar reduction in greenhouse gas emissions as battery electric vehicles, only when considering renewable hydrogen, which is still not widely available in Europe. When instead considering natural gas hydrogen, their emissions are only 26% lower. And I'll pass the word to Georg Bieker for the policy considerations.
Thanks a lot, Marta, for presenting the results of the study. For the policy recommendations, I would like to make 4 or cluster them in four slides. The first is about the broader big picture relevance of that for the CO2 standards. And here we clearly see that also when considering the fuel, electricity, and the battery and vehicle production, BEVs have a large emission benefit compared to the other powertrain types. And we see that BEVs in particular can reach the climate target or help to reach the climate targets of the EU in the transportation sector, whereas ICVs, hybrids, and plug-in hybrids are not able to to meet the long-term emission reduction targets. For fuel cell electric vehicles, we could see that it really depends on what type of hydrogen is being used, whether or not they allow to reduce emissions as much as BEVs. For BEVs, again, we see large emission reductions already when considering just the average electricity mix, whereas for fuel cell electric vehicles, we really need to fuel them only with green hydrogen to get to similar emission reductions. Then, when considering the development of the fuel mixes, we do not expect large changes there, and therefore ICVs, hybrids, and plug-in hybrids will mainly rely on using fossil fuels also during their lifetime, whereas for electricity powered BEVs, we see that the share of renewables is continuously increasing and results in this large benefit. We in particular looked here at a scenario with very optimistic shares of advanced biofuels, and we could see that the impact was not really large, not really changing the picture. When it comes to e-fuels, that is in theory also a possibility to reduce emissions, but we need to see that these fuels could be used then only in vehicles that are e-fuels vehicles only, so they would not also be available for the average fuel mix. But in any case, it's very uncertain if the volumes of these fuels would be available in the future in large enough quantities to not only decarbonize aviation and maybe shipping, but also have some available for the transport sector, which at this point is very uncertain in terms of availability, but also in terms of costs. So at this point, when discussing the CO2 standards, we see our results here largely supporting the phase out of combustion engine cars and hybrids by 2035. Next slide, please. Then as a second part, of course, it makes sense to also look at other components of the life cycle emissions other than just the tailpipe emissions. And here we see several complementary policies that can help to reduce the broader environmental and climate impact of vehicles. Examples here are the battery production carbon footprint provisions in the battery regulation, but we can also maybe now with the IDAA include sustainability criteria for vehicle purchase subsidies or for public procurement. So these are options where the vehicle production emissions could be reduced or incentivized to be reduced. Then for BEVs in particular, we see that energy efficiency standards could really help to reduce the electricity consumption, thereby the emissions coming from that. And then, of course, for the power sector, we see that the emissions trading system has been very effective in the EU to reduce emissions of the power sector. And this is a policy that we see as being effective also going into the future to decarbonize the electricity mix. Then on the next slide, we want to bring our perspective on life cycle assessment-based regulations, which are being discussed and could maybe in the long term be a way to cover all of these emission components in just one metric. But as shown in this study, there is quite some sensitivity of the results of LCAs to some assumptions. We highlighted 5 factors here, and they could in principle be more. So there's always a risk that a methodology that is not using representative values for all these factors, that this could disproportionately benefit powertrain types that do not allow the long-term decarbonization potential. So especially in the transition period between powertrain types that we are in today, we see that there's quite a risk of going to a life cycle assessment-based methodology when this is considered to be replacing the CO2 standards. Then we see as a second point a large administrative effort for setting up such a system. All the companies would need to report the emissions across the whole supply chains, and we would need to agree on decarbonization scenarios for the power sector and maybe also for the fuels mix. So there's a lot of effort that this needs for the companies to report, but in the end also for the governments and for the regulators to verify and to make sure that the emissions reported by the companies are correct. So there's when today there's a lot of talk about reducing the administrative burden for companies, going to a life cycle assessment based would result in the opposite and actually increase a lot the administrative burden. And then the last point here is that it takes a lot of time to develop such a standard. It would require several years of reporting data from manufacturers. Maybe this will start next year when companies can report voluntarily their emissions based on the methodology that is being developed by the European Commission. But then it would take, as said, years to collect data and to be able to establish maybe a baseline and then also a pathway on how fast these emissions can be reduced. So this is something that can be effective maybe on 10 years from now. And this is the time frame after the phase out of combustion engine cars, so maybe 2035 plus. But as said, it still requires a lot of methodological considerations, but also a lot of administrative burden. And then maybe the last point here on the next slide is restating what was already said by Marta, that there's a large need to harmonize life cycle assessment studies. We have seen in the past again and again that there are new studies coming out and getting to different results. And the factors we highlighted here in this report, also in the presentation today, the 5 ones here really help to understand why the different studies come to different conclusions. Yeah, I think they were presented already twice or 3 times. So this is like really the key thing here, to look at all these 5 factors. And when we want to have comparable LCA studies in the future, there's a need to harmonize methodologies. And so therefore we welcome very much the efforts at the European Commission level currently to develop CO2 methodology, but also on the UNECE level to develop an internationally harmonized methodology. So thank you very much from my side.
Thank you both. Right in time. We still have around 15 minutes to respond to your questions, so please send them in the panel that you have on your Zoom window. We already have many questions, so we will try to go through them and respond as many as possible. But of course, you have seen that we have our emails available. You can always approach us for follow-up questions. First, I will just respond that yes, the slides will be made available. You will receive them after this event. And yeah, let's go for the questions about content. So I see that there are many questions about plug-in hybrids. So maybe I will start with that one. This is a good one, a very straightforward one. Why don't you see a higher emissions reductions potential for plug-in hybrids? Maybe I'll pass this question to Georg, if you want.
Yes, sure. We at the ICCT did some studies on the real-world fuel consumption of plug-in hybrids already in the past. We did studies in 2020 and 2022 together with Fraunhofer ISI. We already back then found that the fuel consumption of plug-in hybrids is much higher than the values reported in WLTP. In the meantime, also the European Commission started collecting data on plug-in hybrids, and based on, I think, 2 million vehicles by now, they pretty much find the same deviation that we found on a smaller sample size. And this is already considered by the European Commission to change the electricity drive share assumption in vehicles that are newly type approved in the EU. So there's quite a large evidence that the electric driving shares of plug-in hybrids in type approval in earlier cycles were not realistic, and we've seen that the fuel consumption is much higher in real world. And this is due to several reasons. The main reason is just that electric vehicles are not charged as much as assumed. So the WLTP values initially optimistically assumed that the plug-in hybrids would be charged once a day on average, and then start the day with a fully charged batteries and drive on electricity as much as possible. But we find that this is not representative. On average, maybe people charge only 2 or 3 times. No, sorry, charge only every 2 or 3 days. And this just not charging that much results in the higher fuel consumption. We can see that they still offer a benefit compared to conventional cars. So plug-in hybrids are not a bad thing. They can help, but only in the short term, and they do not allow the large decarbonization potential as for BEVs.
Thank you. I think this answers several of the questions that we had in the queue. Maybe I will move to another question, this time about batteries. Do you account for batteries being produced in China? This is a more methodological question. Maybe Marta, you can address it.
Yeah, thanks. Yes, we do. So we consider the batteries being used in Europe, and we see that on average about 30% of the batteries are produced domestically, and the remainder would be produced so in China, but also in South Korea, Japan, and the US. So we did account for that in the study.
Thank you. More questions about what is considered in the analysis. Does LCA consider the energy emissions in production of renewable energy and hydrogen technologies? Maybe Marta?
Yeah, I can take that. Yeah, we do account for that. And as we mentioned already, for the electricity being used in vehicles, we also account for the production emissions, so the full life cycle of electricity production too. So taking into account the power plant construction, the grid connections, and so on. So that is included. And the same for hydrogen, we include everything, including the manufacture of the fuel, the hydrogen system.
Mm-hmm. Thank you. Then we have a question about battery lifespan. How did you consider the battery lifespan, and is it considered that they will be changing during the EV lifetime? If yes, when? Maybe that's a question for Georg. I don't know if we can. Yeah.
Yes, sure. Good question. At ICCT, we generally assume that batteries will last for longer than the vehicle lifetime. So we see that there are warranties that last for maybe 8 years, and this is also reflected in minimum durability requirements as in the Euro 7, for instance. But we see these values rather as like warranty values, really, to ensure or to exclude production failures. When looking at the real world data of the battery durability today, which is increasingly becoming available, we see that batteries can be expected to last very long. We see that the degradation in battery capacity for vehicles on the road for 10 years is still quite low. So we can interpolate that and expect that also in the future the batteries will last for a long time. And then also there's a lot of data from lab tests that do very rigid testings of the batteries, charging them very fast again and again, and they find that lithium-ion batteries produced today last for 3,000 to 5,000 equivalent full cycles, and this translates into a lifetime of more than 1 million kilometers, so 4 times more than what we assumed here. So yeah, as said, we consider that the battery will last as long as the vehicle, and this is, to my understanding, also is what the companies are currently are expecting from their vehicles.
Great, thank you. Let's see if we can go through so many questions. The next one is about temperature effects on BEVs. Were cold temperature effects considered for battery electric vehicles? And then it explains that at cold temperatures, BEV energy consumption can be significantly increased, leading to increase in use emissions. Maybe Marta, this is something for you?
Yeah, I mean, we consider real world fuel and electricity consumption, so that is included. It includes the average conditions in which these vehicles are driven. So yeah, extremes would also be included.
Great, thank you. Another question about what is considered. I would like to ask whether the emissions associated with raw material extraction and processing were considered to estimate the regional emissions intensity of battery production. Also very concrete, maybe Jason.
Yes, so that's all accounted for. So in general, the battery production emissions are based on the GREET model, and we modified the GREET model according to like the regions where the battery are produced, and that includes also changing the regional supply chains, let's say for nickel, for example.
Thank you. And what is the evidence about the longevity, specifically of plug-in hybrids and BEVs? And he comments that I hope my BEV lasts 20 years, but perhaps this is a hypothesis at the moment. I don't know, Georg, you already have touched on this, but maybe you want to address it again.
Yeah, or maybe I can add more thoughts on this. So when looking at the vehicle itself, at least for BEVs, the powertrain is much less complex. So just looking at the electric motor and all the components, one can expect that the durability is actually larger than for combustion engine cars. It really comes down to the battery, whether the battery will last long enough. And yeah, I think I commented that already in length. For the plug-in hybrids, I guess that's a different question actually, because of plug-in hybrids, the powertrain type is very complex. You have a combination of two powertrains, so that makes it also faster to age. But then also we see that even when plug-in hybrids are not charged as much as they could be, they are still charged much more often than battery electric cars. So for plug-in hybrids, we see that this durability of the battery could be more questioned than for BEVs, because it's a small battery that needs to be charged again and again and again. And there you could, in principle, reach these like 3,000 to 5,000 cycles that I mentioned earlier.
Thank you. We have many questions about methodology. And there is one question about how were the RDE calculated? Did you take data from onboard fuel consumption meter? This is a question that can be also answered very quickly, right? I understand.
Yes, so it's based on the data that the Commission publishes from these OBSCMs. So yeah, this is onboard fuel consumption meter data that is considered here.
There is also a general question about forecasts for grid decarbonization. I don't know if you can answer to this. How confident are you in the forecast for grid decarbonization, I guess, for Europe? Maybe Marta, you can address.
Yeah, that is a good question. I mean, these are in the end forecasts, so there's always a degree of mistakes in the forecast, but we see that they are quite consistent in the decarbonization foreseen. And we see actually that, so this 2025 update of the LCA that we did compared to the 2021 study, already the real installation of renewables is higher than what was forecasted 4 years ago. So the battery electric vehicles are getting cleaner faster. So we see, due to market dynamics and incentives that are there, the uptake of renewables is actually faster than that was foreseen in the past. And so we feel that, the forecasts going forward are pretty consistent again in keeping with this trend.
Thank you. We have one question about batteries. Would the following scenario impact the LCA analysis? Impact of solid-state batteries with longer range and sodium batteries, and battery replacement scenarios to increase the life of BEVs and PHEVs. Maybe Georg, you can help with this?
Maybe starting with the last one first. When you look at the bars and the small part that the battery reduction plays there, in the end, it doesn't make that much of a difference whether or not you consider that the battery needs to be changed or not. The overall trend is very much the same. And you can just like double the size of the dark yellow bar to see what would be the impact of that. For sodium-ion batteries, it really depends on what type of sodium-ion batteries we're talking about. So the battery chemistries that are currently being produced for sodium-ion batteries in China, there it's a bit uncertain actually if the emission intensity is lower or higher than for lithium-ion batteries, because they can in principle use like less emission-intensive materials, but those using these less emission-intensive materials are not the ones that are currently being produced. The ones that are currently being produced actually also use nickel and other minerals. So it really depends a bit on what we talk about for sodium-ion batteries. And for solid-state batteries, we expect that the emission intensity would be higher than for lithium-ion batteries. And this is because they in the end need more lithium, and this also contributes to a higher emission intensity per kilowatt hour.
Thank you. There is one question about rebound effects, increased travel to lower operation costs. Do the models also capture potential rebound effects? Did the models only assume same travel distances as current travel behavior of internal combustion vehicles, or how that can rebound effects be considered? I don't know if this can be answered by any of you.
This is a very interesting question. It relates maybe also to the observation that different powertrain types today have different use cases. For instance, a diesel car is driven more mileage than a gasoline car, maybe for similar reasons actually. For this analysis, we consider the same use case. So to make a fair comparison, if a consumer is going to a shop and wants to buy a car, there is one specific use case of that user's demands, and this is what we have had as a basis here for fair comparison. So all the vehicles are compared with the same usage profile, and this is the average, considering like this 12,000 kilometers per year and then a 20-year lifetime.
Thank you. We are approaching our time, but I think we have still some time for one or two more questions. I think we have this question. I'm not sure if we have answered. Please let me know. Is there some consideration related to recycling the batteries or replacement and its impacts in the LCA? Marta, you have.
Yeah. So yeah, we did consider both. So we considered the end of life of the battery, and we did not consider though any replacement in this. Again, for what Georg was saying before. We see that the batteries would last for more than the lifetime of vehicles, so we did not include replacement of batteries for this LCA.
And we have a very open question. I don't know if you maybe, Georg, you can answer to this, but do you think that it's really possible, I guess this comes from skepticism, to come up with a standard set of assumptions to LCA models that would be agreed by all players?
Yeah, I'm involved in several formats that try to to get to a standard. I don't know. I guess we need to see. I think like with the European Commission now having the task to develop methodology, I think they have to do that, and they will in the end decide for some parameters. But I'm sure that not everybody would be happy with the parameters they agree on. They decide in the end. Yeah.
Great, thank you. I think we are just in time to close the webinar. We have many questions, but it's the time. So just remember that you will receive the slides and the recording, which will be made available on our YouTube channel. And thank you everyone for participating. Please don't hesitate to reach out to us if you have further questions. And remember to also follow us on our social media channels and subscribe to our newsletter if you haven't yet. So thanks again. Thanks again also to the speakers for your time. And we hope to see you soon.
Thank you for your interest.
Thank you.